So next we want to take some derivatives of these functions. So to do that, let's compute these derivatives by hand. And the reason we want to do that is when we're solving partial differential equations, we don't always know what the solution looks like. That's the whole point of trying to solve it in a computer, is it's very hard sometimes to get a feel for what these things look like on paper. So if you can solve it in a computer, sometimes you get a better idea. But if we don't know what the function looks like, we don't really immediately, we can't take its derivative by hand. So let's test it in the setting where we can take derivatives by hand. So here, the x derivative of this guy is just, well, e to a power is just that same thing times the derivative of what's inside by the chain rule. And in fact, we can shorten this up a little bit. This is just u again. So if we wanted to be kind of cheeky or save a little computational time, we could put a u here. But of course, both of these are vectors. So if I try to multiply these together, if I run it, I get incorrect dimensions for matrix multiplication, which seems like kind of a funny error until we remember that, right, both x here, and so therefore cosine of x, and u of x are row vectors. And I don't have a good rule to multiply row vectors. Of course, what we wanted to do is to multiply them together. So we use component-wise multiplication. So I use a dot times there. Excuse me. So that's u of x. If you want to check what the second derivative is, I've computed that here. Hopefully that should come up. Yeah, so you can double check, but I believe this should be the second derivative there, just again by, well, chain rule and product rule. Great. Okay, so we have some derivatives that we can test with, and we can see what's going on. Of course, these are the exact derivatives, so we would like to see if we can recapture these fairly well with Fourier transforms. Okay, so let's see how to do something like that. So in order to take a Fourier transform, you might know that, right, so our Fourier transform at each point looks like something like a sum over k of, say, u hat k. I'm just sort of writing this heuristically here, times let's say exp of I times k times x. So if I take a derivative of this function, and if I'm allowed to commute the infinite sum here with the derivative, then what happens, so if this is u, if u is equal to this, then u sub x, which I'll just take to mean the x derivative there, is going to be, well, just I times k times that x, right? Maybe we'll do something like that so it looks a little bit better, right? So I times k times x is what we get. So we want to replicate that functionality in Matlab. And so notice what's going on. We need to know what the kth index is. And remember, the index can be positive or negative. And we want to multiply the kth Fourier coefficient by that, and also multiply by I. So let's make one more note in Matlab. Actually, if I try to multiply by I, let's just say I did something like u is I times u. Matlab will do that, but it doesn't really like it because it says, let's see if we can get it to say, yeah. For improved robustness, consider replacing I by 1i. So 1i is kind of Matlab's preferred way to write the imaginary number. Okay, so in Matlab, 1i instead of I. Oops. Okay, great. So what really remains is to find the index here. But we already investigated that a little bit earlier when we were looking at the transform of sine. So here we have the 0th index, first index, the second index, and so on. So we just need to replicate that in Matlab. And to do that, so we'll take, let's see, I had this here, yes. So Matlab stores its indices in the following way. Maybe I'll put some commas here. So we start off at 0, and then count up through n over 2. It turns out it's actually n over 2 minus 1, and then 0. And then after that, we start with the negative indices. So this starts at negative n over 2 plus 1 and counts all the way up in positive steps, all the way up to negative 1. So let's get a feel for what that looks like. So, and the whole result gets multiplied by 2 pi divided by the length of the domain. Our length of the domain is 1 here, so maybe we'll just leave that off for demonstration purposes. But if you were to use a different length of the domain, you would multiply by 2 pi over L. So going back to our example of 16 grid points, let's take a look at what this K looks like. So let's have Matlab tell us K prime. Run it. See there, Matlab starts counting. So the first entry is wave mode 0, all the way up to wave mode 7. And then there's a 0 here. I'll explain more about that in a minute. Technically, this should really be thought of as the 8th index, and then negative 7 up to negative 1. So those are our indices. All right. The reason for this, so how are we going to take a derivative? We'll just take this K multiplied by I, and then multiply it by U hat. So let's see that in a minute. But the reason for the 0 index turns out to be a little bit important. It's because when we're expressing the discrete Fourier transform, and we're using an even number of grid points, we're using powers of 2 here, so we typically have an even number of points. There's going to be the first index, the 0th index really, is always the average of the function. So when we're taking a derivative, the derivative of the average is a constant, so the derivative of the average is 0. But not only that, the average of a real valued function is 0. That means that one of these things is going to be a real number. By the normal symmetry conditions in the Fourier transform, that must mean if we have 16 of these entries, there must be another real one. And if you write out the Fourier transform, you find out that you get something. So you'll get, if you write them out with complex exponentials, you'll get one last entry. The 8th entry will only be pure imaginary. That means it'll be a pure cosine. So when we take the derivative of cosine, we get sine. And in particular, we get not just cosine or sine, but the last entry in there will be cosine of n divided by 2 times x. Or if you want, maybe it's clearer to write that as n times x divided by 2. N divided by 2 is the last representable frequency in a Fourier, in a discrete Fourier transform with n grid with even number of grid points, n grid points. So if we have something like that, we always get this last real one. Now its derivative will be sine, and if we plug in all of the all of these points along sine, we get a function which is identically 0. So that means that when we're taking these derivatives, we will always be multiplying by 0 in the in that last entry. So this is the this entry is sometimes called the Nyquist frequency. Must y by 0 in odd number. Because an odd number, if I take one derivative, I have a sign, 3 derivatives, I'll have a sign, and so on. So, okay. Again, if that's a little bit confusing, that's okay. Just take this, we'll just take these k's to be the wave numbers for now. And then let's choose, we can either define it separately. I often just define it as ik. So this will be 1i times k. All right, we could have put the 1i up here, but we'll keep it as is for now. And then, so let's compute ux approximate to be, well, we've got our Fourier transform, or do we? I've erased it. So we'll take u hat to be the FFT of u, like that. Let me get a little more on the screen here. So u hat will just be I times k. We need a dot times because they're both vectors, times u hat. All right. So if we've done everything correctly, we should see that these look pretty darn close. So if we take so let's plot u, say x comma u. And then we also want to plot so this is, I should really call this u hat, ux prox hat, because this is still in Fourier space. So if I want to come back to physical space, one way to do that is to use the IFFT, the inverse Fourier transform, inverse fast Fourier transform, which works. The algorithm is very similar to the FFT. And so I'll put here u hat approx. And it turns out, since we're starting with real variables, it's a little faster and a little more accurate if we also hand it this symmetric tag. So that will allow Matlab to exploit the symmetry that comes from when you're starting with something real. If you're using something complex, like you're solving a Schrodinger equation or something like that, you do not want to use this tag. That will give you erroneous results, most likely. But since we're dealing with real variables, this is a nice tag to use, a little faster, a little more accurate. Okay, so we'll plot x comma u. That's our, sorry, I guess we should really plot x comma u of x. We want to check the derivative. And then let's put hold on and plot x comma, well, this ux approx. And let's plot this one with maybe dash O's so we can see things, and then this with dash star. Oops, dash star. There we go. And let's do axis square. Okay, we take a look at this. Pretty darn close. They look like they're almost right on top of each other. If you want to see it maybe a little more close up, maybe we could do something like this, subplot. So let's call this 1, 2, 1 again. So we'll have that plot on the one side. On the other side, let's plot the error. So to plot this, we'll take maybe the absolute value of u approx minus ux. All right, so we run that. We see our error here is about 10 to the negative 7. So, at least 6 decimal places of accuracy. This is pretty darn good for, only 16 grid points. For instance, compare this with something like finite differences, where, your accuracy might be 10 to the minus 1, 10 to the minus 2, something like that. So this is a pretty nice, nicely accurate setup. If we increase the number of grid points, so let's double the number of grid points there, we're already at machine precision. That's part of why I wanted to work on something so low. We have this very, very fast convergence. Now you might ask, great, okay, so you might say, well, 10 to the 2 to the 5th is maybe all that we need here. But something kind of funny happens if you increase the number of grid points here. So there's 64, here's 128. The error actually starts to increase a little bit. Let's go all the way up to, say, 2 to the 15, so that's like 33,000 or something. And our error has degraded a bit. It's still pretty low, 10 to the minus 11. But yeah, why has it gone up, right, if we're using more grid points? And basically the answer is our error was already so low down at machine precision, down here at, say, 2 to the 5 only, that as we increase the resolution, we are adding more and more round off error, which accumulates as we take more and more grid points. So this isn't really say a bug. This is just how floating point numbers work. we don't really have a good way around that. And the fact that we're getting down to machine precision with only 32 grid points here is pretty remarkable. So any other numerical algorithm will suffer from this same type of difficulty, that eventually you have this diminishing returns where your round off error starts to catch up with you. But anyway, pretty nice to see that machine precision. Now let's go just a little bit further, and we'll see second order derivatives, because they behave a little bit differently. So here we've got ik, and maybe I could even call this something like, say, first derivative, or something like that. For the second derivative, you might think, well, I'll just take the derivative twice. And that's almost right. But remember this thing about this Nyquist frequency, that the last entry is cosine of nx, and its odd number derivatives will therefore be sines, which will be identically 0 on the grid that we have. Okay, so for that, that's why we have this 0 here. So for the second derivative, we have to modify that slightly. And maybe I'll just write it in here. So I'll write second derivative is this one. And then, so if I take a second derivative, I'll have 1i times 1i. Well, I times I, that's I squared. I squared is -1. So we can just build a negative in there. But then this Nyquist frequency does not die. So we can let the counting run all the way up to n divided by 2 in this case. And we would still have our, if we had domain, maybe we should bring this back. I just wanted to show you what happens in this case. L is equal to 2 pi, and there probably shouldn't be any round off error from this, but just in case I covered it up. So this one should be squared. And then, of course, we want to square this bit as well, being careful not to square the negative, of course. To square this vector, we just use dot times. Okay, great. And I'm not worried about, the most efficient way. You could, of course, factor this out and dot square the whole thing or whatever. Right now, we're just trying to write this in place. Okay, so we have something like this. Maybe we should just write that our first derivative is, we don't have this extra term, something showing up there. I like to also align these a little bit so I can just kind of visually compare them. In case I have an error in my code or something like that, it's a nice way to quickly check. Okay, so there's our second derivative. I've used the shift enter to have Matlab correct that everywhere for me. And then we can just copy this bit. So we'll call that uxx approx hat, uxx, xx, and then our second derivative operator show up right here. Great. So if we then, maybe we'll have an extra row in our subplot. Oops, I guess I should undo that. We'll copy these. Plot again. Oh, I guess I want all of these to be square. And for these, we'll plot the second derivative, the error in the second derivative. Oops. See how that looks. Oh, and I need to call that, I guess this is plot number 3 and plot number 4. Okay. And something is not sure. Because I have a 1, 2. This needs to be a 2, 2. There we go. Okay. So it might be good to label these so we can be sure of what's going on, but we're just trying to do something quick here. So on the left, we see in physical space the derivatives there. On the right, we see them. We see the error between these two. Here's a second derivative and the error in the second derivative. I would say that's pretty nice. So let's stop there.